Last time we talked about different navigation techniques. Today we'll first have a brief overview of GNSS so that you can start working on the project. So basically, I'll tell you some important terminologies used in the context of GNSS so that you know come across those terms on the website or in any article that you need to refer to understand them properly. Okay, and after that, if time permits, we'll start the discussion of different navigation coordinate frames that we'll consider in this class. So first, let's have an overview of GNSS. So the full form of GNSS is Global Navigation Satellite Systems. So this represents all the satellite constellations, navigation satellite constellations of different nations all over the world. So the first GNSS system developed was GPS, Global Positioning System. This is fully operational of the US. Then there are other systems as well. For example, Russia has GLONASS. Then the European Union is developing its own system, and UK is also part of it. It's called Galileo. I was writing EU here. China has its own system called Beidou. Okay. So these are 4 global systems. Okay. So they have global coverage, meaning anywhere in the world the user can receive signals from these satellites. Then there are regional systems as well. QZSUs. Stands for quasi semi satellite system. So this is for Japan. So QZ QZSS is not an independent system. It basically uses GPS satellites and augments the GPS service with some additional satellites to improve accuracy. Okay, so QZSS satellites are used alongside GPS satellites. The second regional system is IRNSS, Indian Regional Navigation Satellite System, IRNSS. It is also called Navigation with Indian Constellation. Okay, NAVIC. This is an independent regional system. Okay, it does not depend on any other constellation for service. Okay, so unlike QZSS, IRNSS or NAVIC is an independent regional navigation satellite system. Okay. There are some other augmentation systems as well, but for the overview purposes, I am not going to talk about them. When we'll have a formal introduction of GNSS, I'll briefly mention about those augmentation systems also. These augmentation systems are different from QZSS, okay? So they are meant to improve accuracy and reliability of GNSS services. So all these different systems are together represented as GNSS or Global Navigation Satellite Systems. Okay, quickly draw this figure. Any GNSS system has three segments. Okay, the first one is called the space segment. The space segment is the constellation of spacecraft that are orbiting the Earth and transmitting signals towards the Earth. Okay. For example, GPS currently has 31 satellites in orbit. Okay. Then IRNSS has 7 satellites, but I recently came to know that only 5 of them are operational. I'm not sure about the status of the other 2. So basically, a space segment consists of the constellation of spacecraft that transmit signals towards the. I think one of you is unmuted. Somebody who joined recently and not muted. Mute yourself. So they transmit signals towards the Earth. The second segment is called control segment. The control segment is actually responsible for maintaining the constellation. Okay, so they have several ground stations, network of stations that monitor the satellites. Okay, so they continuously track the satellites, make sure satellites are healthy. If a satellite is not healthy, then they need to take appropriate action. They also do station keeping maneuvers where they remotely fire thrusters to make corrections to the orbit so that satellites remain in their designated orbits. And they also upload important information to the spacecraft. Okay, so last time I told you that for GNSS to work properly, all the satellite clocks to be synchronized to a common GNSS time, right? So they are responsible for maintaining that time. And they also, based on data collected from satellites using stations spread all over the world, depending on what constellation it is, uh, they actually estimate different parameters, orbital parameters of the satellites, and also the satellite clocks. Then they upload the orbital parameters to the satellites and remotely steer the clocks. Also upload the clock parameters, the satellite clock errors from GNSS system time. And then this, many other parameters are also uploaded. I'm just giving an example of few of them. Now these parameters, this information is transmitted by the satellites in the signal. Okay, so the control segment is basically responsible for maintaining the constellation, making sure satellites are all healthy and they are transmitting healthy signals so that user gets reasonable good accuracy. So this is the second segment. Then the third segment is called user segment. So user segment is basically the end users that receive signals from the satellites and then process the signals to get position, velocity and user clock error from GNSS system time. Now this is a passive system because the users do not communicate with the satellite. Users just receive signals from the satellite. The only segment which can communicate with this, the spacecraft is the control segment. So they can have two-way transmission, but the user segment will have only one-way transmission of signals from the satellite to the user. Okay, so these are the three segments that are present in all these different GNSS systems. So that it is GPS, GLONASS, Galileo, or Vedu, or Navi. So they all have these three common segments. Okay, but how individually segments operate may vary from constellation to constellation, but they all have these three segments. Okay. Now, let's also briefly talk about this GNSS signal structure. Again, I will not go into much detail. The signal has three components. The first one we call pseudo-random code. Pseudo-random code. So it's basically a series of pulses. It need not be always 1010 or plus minus 1 like that. It can have multiple zeros and ones and then again 1. So basically a series of pulses, and each pulse is called a chip. So basically the code is a series of chips. Okay, now we can have two representations for chips, either plus minus 1 or 0 and 1. So in 0 and representation, plus 1 is equivalent to 0 and minus 1 is equivalent to 1. So basically they can take binary values which we can represent as plus minus 1 or 0 and 1. Okay. Number of chips in a second. It's called chipping rate. Okay, now different constellations have different types of different pseudo-random codes with different parameters. Okay, now even within a constellation we can have different pseudo-random codes. Okay, with different shipping rates. Now in this class we are mainly interested in GPS and Navi. So they use different codes. The simplest one is called course acquisition code. CA code. Okay. Now for CA code, the chipping rate is small, 1.023 megahertz. Okay, so there are codes that have higher chipping rate. So 10.23 megahertz is also possible. Now it is called pseudo-random. So why pseudo-random? Because if you see the code over a short period of time, you will see a series of zeros and ones, and the series will appear to you as random. But actually, the codes, the series of zeros and ones, are determined based on some algorithm. Okay, so they, although appear random, they are actually not random. That's why it's called pseudo-random. So they have a pattern which repeats after a certain interval. Okay, the interval at which the pattern repeats is called code period. Okay, that's why we say pseudo-random. Now you ask why we required pseudo-random code. Now this pseudo-random property provides a very interesting feature. Okay. So if you take one code and try to match it with the code of another satellite, so basically you are trying to match two codes, each from one satellite. Okay, you will find that they do not match. If you try to match a code with itself, you will find that there is a very good match. So this way, by using different codes, we can uniquely identify a satellite. So we know which satellite should transmit what code. So when we retrieve that code in the signal, we'll know that that satellite signal has been received. So this is how, using this pseudo-random property of code, we can uniquely identify a satellite. So this is a sort of a key which allows us to identify a satellite. In addition to this, the pseudo-random code can be used to determine range to a satellite. So we already discussed that GNSS works on the principle of ranging, right? So we need to measure ranges to the satellites. So using the pseudo-random code, it is also possible to determine ranges to the satellites. So it has two basic functions. One is identify a satellite. Second is determine range. Okay. And I think for the time being we will note only these two properties. Okay. Then the second component is called navigation data. Navigation data is also a series of plus minus ones. but these pulses are called bits. Okay. So it's basically a low frequency train or series of pulses. We have seen that in case of code, the chipping rate, number of chips in a second is on the order of 2 megahertz, 1.023 megahertz per second. Whereas navigation data is a low frequency train of pulses. Again, it varies from constellation to constellation. I am telling you about GPS and Navi. So 50 hertz, the most common form of data, navigation data. Uh, it has a frequency of 50 hertz. It will be on that order. 50 hertz means you have how many pulses in a second? 50 pulses in a second, right? And what is the duration of one pulses?
1 by 50.
1 by
50.
50. 1 by 50, that will be 20 milliseconds. So each pulse is of duration 20 milliseconds. Okay? So this is how you represent code. In navigation data, you have to represent with longer pulses, much longer pulses. Okay. But again, this is a series of plus minus ones or zeros and ones. And what does it contain? It basically transmits all the information pertaining to the system, GNSS system, spacecraft, and other things. Timings, GNSS time, then orbital elements. So each satellite will transmit its orbital elements. Then satellite clock error, from GNSS system time. Now each GNSS system has its own time, okay? So a GNSS system can also transmit its time offset from other systems. For example, Navi transmits GNSS system time offset from GPS time, like that. Okay. Then it also transmits information like spacecraft health, satellite health, and signal health, etc. Okay, so when the receiver receives signals, does all the required processing uh, and identifies a satellite. So how it can identify a satellite, we'll see later. For the time being, just note that receiver knows which satellite will have what code. So it tries to match the code of a particular satellite with the received signal, and then when it finds a good match, and good match is possible when it actually aligns its own replica code with the incoming code. So when it does that matching, does that alignment, it can actually access the navigation data. So without matching code with the incoming code, it is not possible to access the navigation data. Okay. So you can think of the code as a key to the navigation data. Now, next component is called carrier. As the name suggests, it carries information. It basically carries code and navigation data from the satellite to the user. A carrier is a sinusoidal Basically, it's an electromagnetic wave. Okay, transmitted at a radio frequency. Now here we need to define two things. First one, what is an electromagnetic wave, and the second thing is radio frequency. So let me quickly first tell the radio frequency. So radio spectrum, and then I'll define the electromagnetic wave. So radio spectrum is the electromagnetic spectrum with frequencies lying between 30 generally 30 kilohertz to 300 kilohertz. Okay, so this is typically defined as the radio band or radio spectrum. Now, the carrier in case of GNSS has a frequency in this band. Okay. Again, different constellations have different radio frequencies. Okay, typically the L band, which is between 1 and 2 gigahertz, is chosen for satellite navigation (GNSS). IRNSS is the only constellation that has carrier frequency in the S band also, but S band has other issues. Okay, so it can interfere with other frequencies. For example, it's close to Wi-Fi frequency, so there is a possibility of having some problem with Wi-Fi signal. This is why ISRO has, and few other reasons are also there. ISRO has decided to have another L. So basically, one frequency is in the L band. GPS has in L band. GLONASS, Galileo, they all have carrier frequencies in the L band. So IRNSS has one carrier frequency in the L band. The second one was in S band. But recently they decided to have one more carrier frequency in the L band along with the existing two. Okay. Next, what is an electromagnetic wave? So basically, an electromagnetic wave is a synchronized oscillation of electric field and magnetic field. Okay. So white represents electric, let's say electric field, and green would be the magnetic field. So this is a synchronized oscillation of electric field and magnetic field that propagates in a direction. So it propagates in this direction, propagates in a direction perpendicular to both fields. So this is E field, and then this is, let's call this B, magnetic field, the field strength. So electric field and magnetic fields, they oscillate and they are both orthogonal to each other, and they propagate in a direction that is orthogonal to both the fields. So this is an electromagnetic wave. Now it can be shown using Maxwell's electromagnetic theory that an electromagnetic wave can propagate in a vacuum. So what we do is we uh, we modulate code and data. So modulation, don't worry about modulation in case you do not know about it. Modulation means it's a way of including code and data onto carrier. Okay. So we modulate code and data onto carrier because otherwise we will not be able to transmit the information from far away satellites. So the only possibility is to modulate this information onto the carrier and then transmit the carrier as an electromagnetic wave. Okay, so the primary purpose of the carrier is to transmit information from the satellite to the user. Now, in addition to this, the carrier can also be used to determine range to a satellite. Okay, uh, and it can be shown that the range accuracy that we get from carrier is much better than what we get from the code. However, uh, since the carrier frequency is very high, uh, it is possible to lose track of the carrier. So receiver has to continuously track the carrier. Okay. Now since the frequency is quite high, it is possible to lose track of the carrier, especially when the signal reception environment is not so good, and then when the vehicle is maneuvering, there is a high chance that the carrier tracking can be lost. You will understand this as we go on and talk more about GNSS. But the accuracy, range accuracy that we get from the carrier is much better than what we get from the code. Okay, any question after this? Okay, next we will talk about GNSS measurements. We know that GNSS works on the principle of ranging. So we need to find range measurements to satellites. And since here we are finding 3D position, how many satellites do we require? Minimum? How many satellites do we need?
Four.
Okay. So it depends on whether you are considering clock error or not, right? So if you also have clock error, user clock error, then minimum 5 satellites would be required, right? Now, see, if we, for the time being, if we ignore clock error, we have three position coordinates, x, y, z position coordinates, and we also know that we basically get, four satellites means, if we have three satellites, we have three spheres in 3D, and finally we get two candidate positions, right? Now, in case of GNSS, it can be shown that one of the position is not realistic. So either it will be deep inside the earth or high above in space where the user is not operating. So one of the candidate positions can be eliminated based on this information. Generally, it becomes unrealistic. Okay. So using three satellites, if we ignore the clock error, using three satellites, we will be able to determine the position, because one of the positions, two candidate positions, can be eliminated because that would not be realistic. So if we ignore the user clock error, minimum 3 satellites would be required. But we also have clock error, right, which we need to estimate. So a minimum of 4 satellites would be required to determine the user position and clock error. This is clear to everyone? Why I said a minimum of 4, not 5, even when the clock error has to be determined? This is clear to everyone?
No, ma'am, can you repeat once more?
Okay, so do you understand that without the clock error, minimum of 4 satellites would be required to determine the
Yes,
user
ma'am. Yes, ma'am.
position without
Yes, ma'am.
ambiguity. That is
Yes, ma'am.
clear to you?
Yeah, that part is clear.
So one of the positions would be unrealistic. So it can be shown that either it will be within the earth. So within the earth there cannot be any user, right? Or it will be high above in space. Okay. So generally we use GNSS for terrestrial users or for low Earth orbit satellites. All those work is going on to use GNSS to determine geostationary satellite orbits as well. But generally, you will have information about the user operating region, correct? So based on that information, it is possible to eliminate one of the two candidate positions. Is this clear now? Why we are
Okay.
eliminating one position? So
Yes,
if
ma'am.
we
Got it.
eliminate one position, then we with three satellites we got two candidate positions. One position we could eliminate based on the realistic operating region of the user. So we basically get one position. Now we also have the user clock error. So that is an additional unknown. So we need one more satellite or one more transmitter to determine the user clock error, because you have four unknowns then, right? X, Y, Z, three coordinates of the position and user clock error. So four unknowns, so minimum four satellites would be required in 3D to determine the user position using GNSS signals. We also discussed signal geometry, where we talked about the importance of transmitter distribution with respect to the user and good quality measurements. And there is a higher chance of getting good quality measurements and good distribution when you have more satellites. So if you have more satellites, although there is a minimum number you require, you want actually more satellites because you want to get good accuracy. So you want as many satellites as possible. The more the number, there is a higher chance that you get better quality measurements, and you can also improve the signal geometry. So although the minimum number is 4, we want as many satellites as possible, and this is one of the reasons why other nations started developing their own constellation. One of the reasons. Okay, so we want measurements from as many satellites as possible. That we also know that the range to the satellite is determined this way, right? So this is speed of light. This is reception time, signal reception time. This is also called time of reception.
Ma'am,
Yes.
what is satellite constellation?
Group of satellites orbiting the Earth.
Okay, okay, fine.
It's not one satellite, right? You require many satellites. So basically, a
So each
constellation has a.
country will be having their own
It's not
constellation.
that all countries have their own constellations. I already gave you the examples, right?
Okay, ma'am. Okay.
So this is also called receipt time. Okay, it may not have. I mean, it's not grammatic. It's not grammatically correct. It should be receipt time, but practice is to use this term receipt time. Okay? Then similarly, this is transmission time or transmit time. Okay, so we know that to get the range measurements, we need these two times, right? Receive time and transmit time. And whenever we are making measurements, some error gets added, so we have this epsilon, right? Uh, Now let's denote these two times in this equation as Tr prime and Tt prime. It will be clear to you why I put this prime. Uh, Now Tr prime is basically reported by the clock, user clock, and we know that the user has an inexpensive clock, so the time that it reports is not the correct time. Let's call that time TR double prime plus delta TR. So delta TR is actually user clock error. I'll talk more about this later. User clock error from GNSS system time. Okay, now similarly for TT prime, let's write TT plus delta TT. So this is the true time of transmission. Time of transmission is the time at which the signal started from the satellite, and then since the time is reported by the onboard clock, which will have some error from GNSS system time, and this error is broadcast in the signal. We write TT prime as TT plus delta TT. Delta TT is the satellite clock error. Okay, now if we put these two equations in the first equation, we have R is equal to, and then take the delta terms out. Right? So this is user clock error. This is satellite clock error. Now this is true transmission time. This is true reception time, but I have not put here. You'll understand right. True reception time. Okay. And we assume that the signal travels at the speed of light. So this is the speed of light, the carrier basically, speed of light in a vacuum. So this is 299792458 meters per second. Okay. Now, for about 95% of the distance from this satellite to the user, the signal travels in a vacuum. For the rest, so 95 to 97% depending on constellation. For the rest, 3 to 5% of the distance, it has to travel through the Earth's atmosphere. For GNSS, in the context of GNSS, we divide the atmosphere into two layers, ionosphere and troposphere. So the signal enters the ionosphere at about 1000 kilometers from the Earth's surface. Okay, so ionosphere is a layer of charged particles. So as the signal propagates through the ionosphere, its speed of propagation changes from the speed of light in a vacuum through refraction. Then at about 40 kilometers from the Earth's surface, it enters a layer of neutral gas atoms, oxygen, nitrogen, etc. We do not have charged particles, but we have neutral gas atoms that also refracts the signals, and this propagation speed is different from the speed of the signal, the light in a vacuum. As the signal travels through the atmosphere at a different speed, it reaches the receiver at a different time. Had there been no atmosphere, it would have reached the receiver at some other time. So it needs to spend some extra time. That extra time can be positive or negative, okay? It needs to spend some extra time in the atmosphere. So it needs to spend some time in the ionosphere, it needs to spend some time in the troposphere. Okay? Extra time about the distance. So let's write this TR double prime as TR. So TR would have been the time of reception had there been no atmosphere, plus the extra time the signal has to spend in the ionosphere, plus the extra time the signal has to spend in the troposphere. Okay, so putting this in that equation, we get R as C times TR minus TT plus we have C delta TR minus C delta TT, then we have plus C delta TI, then plus C delta TT plus epsilon. This one is the ionospheric error. So delta Ti is the extra time that the signal spends over that distance. And then multiplying that with the speed of light, we get the ionospheric error. And this is called tropospheric error. Right? So this is nothing but the geometric distance between the satellite and the user. Had there been no atmosphere, the signal would have traveled at the speed of light in a vacuum and it would have reached the user at the end. It is the actual signal transmission time. So differencing the two terms, multiplying with the speed of light will give the geometric distance. Right? The Earth rotation rate also comes into picture, but we will not go into that. So this we can write this term. Now we'll also make some correction. See, so what we are actually measuring here is this one, this the actual geometric distance plus all these different errors, user clock error, satellite clock error, ionospheric error, tropospheric error, and plus some epsilon. So what we are actually measuring is range plus error. Okay, so to represent that properly, the convention is to call it pseudo range. If we have range plus errors, we are measuring range plus errors, we call it pseudo range, and R we use to denote true range. So this we call true range. And if we say xs for a given satellite, xs, ys, zs are satellite coordinates, x, u, y, u, ZU are user coordinates. So this satellite coordinates, these are user coordinates. So this geometric range we can write as x u minus x is square plus right. Satellites transmit their orbital elements in the navigation data. Okay, so the user receiver has the required algorithm to determine this x's, y's, and z's coordinates of the satellite at different times from the orbital elements. So satellite coordinates are known. Once we correctly identify a satellite, we can also find the satellite coordinates. So the satellite position is known. Now in this range equation, the only unknowns are the user coordinates, x, u, y, u, and z, u. These are the unknowns. Okay. Now in epsilon, I already mentioned that while making measurements, some error gets added, which we call noise. In addition to noise, there could be another type of error in epsilon. What is that? Now, when we receive signals from a satellite, it can come directly from the satellite, which we call direct line of sight signal. The signal can also get reflected from some nearby structures, a building, and then reach the receiver. So this symbol is actually for the antenna. Okay, so this together this antenna and the receiver, the other components of the receiver. So together this is the receiver. Now the signal can reach directly from satellite. Signals can also get reflected multiple times, not necessary that it will be reflected only once and then reach the receiver. Depending on the signal reception environment, signals can get reflected multiple times and then reach the receiver. Such reflected signals are called multipath. Okay, now depending on how the signals got reflected and when the signals reach the receiver, in comparison with the direct line of sight signal, these reflected signals can actually mix with the direct signals and provide bad quality measurements. Okay, so reflected signals are called multipath. Okay, and then in epsilon we have noise plus multiplier. Both are statistically modeled. We cannot have any deterministic model for these two terms, noise and multipath. We need to model them statistically. This is estimated. This is corrected based on information given in the navigation data. So we assume that this is corrected. Okay, this can, depending on what type of processing the receiver is doing, this can be determined partially or fully. The ionospheric error may or may not be determined fully. So this can be modeled. If it is not determined fully, then this can be partially modeled using some deterministic model. Then tropospheric error can be modeled again using some deterministic model. Okay. And then we get pseudo range measurements from a number of satellites. Okay, and then we feed all the pseudo range measurements to a filter. Okay, and also provide the models, ionospheric, tropospheric models to the filter, and then the filters to statistically model this epsilon term, and then finally provides this XU, YU, ZU, and then this one. Okay. As I said earlier, you are basically solving equations, but you need to do it intelligently because you have these errors. It's not just solving equations and getting unknowns. Yeah, you do not have exact measurements. You have measurements plus errors. So you need to do something intelligent to get the unknowns and at the same time eliminate the errors as much as possible. This is for position. Now, if the receiver measures the rate of change of rho, the pseudo-range rate, then using the pseudo-range rate measurements, it is possible to find the user velocity also. Okay. So, if we write the pseudo-range rate, so we have R dot, right? Here we have CTR dot. This is called clock drift. Rate of change of clock error is called clock drift, and this will be a function of user velocity. And satellite velocity can be determined from navigation data using the orbital elements. Then we have this one TT dot. This is negligible. Okay, whatever small correction is required is obtained from the navigation data. So we assume that this is eliminated. Then we have C delta TI dot. So generally this is small, so we ignore this. Okay, then we have C delta TT dot. This is also small, we ignore. And then we have an equivalent epsilon term. Epsilon will not be epsilon dot, okay? You will have equivalent noise and multipath contribution for pseudo range rate. So that is represented as epsilon RR. Okay. So by grouping pseudo range rate measurements and pseudo range measurements together, we can find user position, we can find user velocity, we can also find the clock error. This is also called clock bias, clock error, or user clock error, of course, or bias. And this delta T R dot gives clock drift. So if we correct the time that we are getting from that inexpensive clock using this clock bias and drift, we basically go to GNSS system time. So this is why it is said that from GNSS we get position, velocity and time, PVT. Because we are getting user position, we are getting user velocity, we are also correct. We can also find the clock deviation or clock error from GNSS system time. So from that we can derive time. So PVT can be obtained using GNSS. That's all for today. We'll continue this tomorrow, and we do not have much left. So basically next we'll see how the satellites can be represented pictorially. We talked about signal geometry. So from that pictorial representation, we can find the signal geometry and distribution of satellites in the sky with respect to the user. It's called sky plot. Okay, sky plot. So we talk about sky plot because using that software, you will be able to plot this, generate this figure, sky plot. We'll also talk about C over N naught. This is a metric which actually tells what kind of signal you are getting. So this allows us to quantify signal reception environment. I'll quickly talk about this one, and then after that I'll talk more about clock. Okay, and after this we'll discuss the navigation coordinate frames we will consider in this class. So any question? Fine. That's all for today.